Students of Seneca, it's Jono here, and today I'm going to be talking about physical properties of compounds for your A-level chemistry exam. It's going to be wild. It's going to build on some content previously covered in episodes about ionic bonding and covalent bonding, so make sure you check those out and are up to speed so we can hit the ground running. Now, without further ado, as Olivia Newton John would say, let's get physical. So we're going to start with solid structures, and there are 4 key types of solid structures. First of all, we're starting off with ionic. So formed by compounds of metals and non-metals. Any salt is a good example of this structure. So sodium chloride, lithium bromide, magnesium chloride, all great solid ionic structures. Next, we have molecular solid structures, and they are formed by covalent bonding. Examples include ice and iodine, and those are structures formed by covalent bonding. Next, we have giant covalent, and this is another type of structure that is formed by covalent bonding. Clue is in the name. And 2 good examples of this are diamond and graphite. Those are covered in the carbon structures episode, so make sure you check those out to get even more up to speed with giant covalent structures. And finally, we have metallic. This form of crystal is seen in pure metals. So we've got magnesium, sodium, aluminium, whatever you like. So those 4 types of solid structures again are metallic, giant covalent, molecular, and ionic. So those are the 4. Make sure you know them. Next, we're going to go over some properties now. The properties of solids depends on their crystal structures. So we're going to start with metals, and this is covered in metallic bonding, but we're going to consolidate it here. Metallic metals consist of a sea of free electrons surrounding positive ion cores. The strong electrostatic attraction means metals have high melting points. The melting point of a metal depends on the number of the electrons it donates to the sea. The free electrons allow metals to conduct electricity as a solid. Metals can also conduct electricity as a liquid. Wild. Metals do not generally dissolve in water. This is because many will react with water to form metal hydroxide. Like if you've ever seen like sodium reacting with water and it goes all like fizzy and crap, like it's not going to dissolve, it's just going to react, and then you get a nice little sodium hydroxide solution at the end of it. Stunning. Okay, now we're going to talk about molecular solids. Molecular compounds have very weak intermolecular forces, but they're really strong people, so don't look down on them. They have low melting points and are often liquids or gases at room temperature. Iodine is a solid at room temperature, but chlorine is a gas, for example. Chlorine is a gas. He's a riot. They don't collect electricity. Some molecular solids may dissolve in water, but many will not. This is discussed later in the session on polarity. I love a preview. I hope you're ready. The suspense is killing me. Next, we're talking about ionic crystals. Ionic crystals have strong electrostatic attraction between the ions. This leads to high melting points. The ions are fixed in place, so ionic crystals cannot conduct electricity as a solid. The ions are charged and so soluble in polar solvents like water. In solution, the ions are mobile and can act as charge carriers. In solution, they will conduct electricity. What are we going to cover next? Boom, giant covalent crystals. Giant covalent crystals have strong covalent bonds throughout the entire structure. This leads to high melting and boiling points. Note, many giant covalent crystals will sublime, which is when you basically skip melting and go straight to a gas. You've got like, honey, I have no time to be a liquid. I am going from a solid, I'm going to a gas. I am not like, no, do not pass go, do not collect $200, like, nah. And the final thing to know about giant covalent structures is they do not dissolve in anything. Absolutely nothing. Could you imagine trying to dissolve a diamond? Honey, life would not be worth living. So, which of these is going to have the highest melting point? Sodium, aluminium, or magnesium? Now, I'm going to be nice and tell you the charge of each of those. Sodium is Na+, aluminium is Al3+, and magnesium is Mg2+. So it's going to be aluminium because Al3+, it's going to lose 3 electrons into that C, and boom, it's going to be really strongly bonded to the positive ion cores. Now, electrical conductivity, let's just review what you need to know about that. solids with high electrical conductivity are molten or dissolved ionic compounds and metals, because ionic compounds, when they're molten or dissolved, the ions are free to move around. The other types of molecular solids do not have good electrical conductivity. So, that was a mouthful. Molecular is really hard to say sometimes. But low electrical conductivity is molecular solids, giant covalent crystals, and solid ionic crystals. Now, what are the four types of solid structure? We've got giant covalent, molecular, ionic, and metallic. Now we're going to compare metallic solids to covalent structures. Molecular solids are held together by intermolecular forces. Intermolecular forces are forces between molecules and they're not bonds. Very important. Do not say they're bonds. They are forces between molecules, okay? And the forces are fairly weak and easy to break. So in melting or boiling a molecular solid, the intermolecular forces are broken, but the strong covalent bonds are not. So when we melt or boil a molecular solid, remember we break the intermolecular forces, but not the bonds. Next, we're going on to talk about giant covalent structures. In giant covalent solids, the entire solid is one molecule. The only forces present are intramolecular forces. Note the difference between between, and intra-within molecular forces. The forces in giant covalent solids are otherwise known as covalent bonds. So covalent bonds are an intramolecular force, and intramolecular forces are much stronger than intermolecular forces. This means that giant covalent structures have a much higher melting point because covalent bonds must be broken. So that's a lot of information. I hope your brains are feeling okay. Let's do some questions to consolidate. For molecular solids, the covalent bonds are not broken on melting, right? What happens in giant covalent structures? So in giant covalent structures, the covalent bonds break on melting. Remember, giant covalent structures don't have any intermolecular forces, they only have intramolecular forces, okay? So molecular solids, do you remember those? How are they made up? So molecular solids, there are covalent bonds between the molecules. They're really strong, but they're not broken in melting or boiling. It is the intermolecular forces that are broken when these substances begin to melt. Okay, and let's finish. Let's go over some characteristics of molecular solids compared to giant molecular structures. So is a molecular solid going to have a higher or lower melting point than a giant covalent structure? It's going to be lower. And is the solid one molecule? Nope, that's a giant covalent structure. So something like a diamond is just one molecule. In molecular solids, the solid is many molecules. And finally, when we melt or boil a molecular solid, we break the intermolecular forces. We don't break the covalent bonds. We only break the covalent bonds when we melt or boil giant covalent structures. So that brings us to the end of this episode. Hopefully it was a useful consolidation of all of the information we've gone over in previous episodes on ionic bonding, metallic bonding, covalent bonding, all of that stuff hopefully is now nicely meshed together. If not, make sure you check out the other episodes to get up to speed. I've been Jono. Well done for being proactive in your work and your revision, and I look forward to joining you in the next episode.